So to deal with some of the challenges of in simplifying the process, right? We are going to be using backward mapping, and to implement it, it's actually a two-step process, right? There's a what we call two-part mapping. First, what we're going to do is that we're going to see look at the how is it that we can map the the image, right, and map it to um, a a a standard geometry, right, a normalized geometry, either a normalized sphere or normalized cylinder or normalized cube, right, and then once we've been able to map it to this normalized geometry, we can then determine and say, okay, well, how do we now, once we have it mapped to this normalized geometry, how can we then map it to the actual geometry that we want to map it to? So it's going to be a two-step process, right? First, we're going to map it to a known surface, right, that we can, for which we have a function, right, that describes it accurately, right? So, for instance, we're going to consider three mappings. We're going to say first, we can map it to a cylinder or a sphere or a box, right? They're very well defined. We have functions for it, right? We have sines and cosines and whatnot that accurately describe our geometry, based on very well-known equations. And as we iterate, right, over the surface area of these well-known geometries, and then as we vary the angles and we vary the radius, right, we know exactly how to generate all the triangles for these various uh, primitive primitive geometries, right? Once, and so what we do is that as we iterate and generate these geometries, we can go back to the source image and say, okay, well, as I am calculating all these triangles in my very well-known geometry, I can go back to the original image, right, and then see how each pixel in the source image, how does that map to my standard mapping geometry, whether it's a cylinder, right, or whether it's a sphere, right? That I again we have the various parameters that allow us to iterate over each one of the x y positions in 3D space and generate all those triangles, and then we can do the map and say, okay, well, as we're iterating over all those triangles, I can go back to my original image and say, okay, well, what corresponds, right? As I'm iterating over this particular triangle that I'm generating for my sphere, for my cylinder and whatnot, what does that represent in my original image, right? So I might decide that as I iterate over u and v, right, which is defines the location of each pixel in my cylinder, I can do a one-to-one mapping of which pixel am I going to grab from the source image and then paste it on each one of my triangles, each one in my fragment shader. I can decide that this particular pixel on the fragment will correspond to some pixel on the image. Same thing for the sphere. As I iterate over u and v that defines the sphere, I can then use that u and v that I'm using for rendering in my fragment shader. I can go back to the original image and say, okay, well, how does that map to the original image, and then decide to use that particular color for that particular fragment in the fragment shader. Also, a box mapping as well. This is a much perhaps a simpler mapping where you can decide to perhaps as you're iterating over a specific a face of the of a box of a cube, then to use that specific image, right? Or you might even have multiple images, right? One per face. Maybe you have six images, spliced together inside the original image, and then as you're iterating each one of the faces, then decide that you want to maybe just iterate a third or one sixth of the original image so that you can use different images per different faces, right? Anyway, but once you've mapped these images on top of one of these parametrized surfaces or geometry, then you can go on to the second mapping, or the second step of a two-part mapping, right? So you've for instance, here the outer circle here represents your normalized geometry, whether you decided to be a cylinder, whether you decided to be a sphere, or you decided to be a cube. Then you map each one of those pixels, right, in your normalized geometry onto the actual geometry, whatever that might be, right? And so there's three different aspects or options, right? You can take a look at the each one of the as you iterate over the various normals that define your normalized geometry, whether this is a cylinder or whether you chose to be a sphere, right? You can calculate what are the normals in each one of your sphere or cylinder, and then project, right? Project how that maps onto the normals of your actual surface, right? And then so you can do the calculation of how the normal of your sphere or cylinder directed into the center of wherever you have your actual geometry, and how does that map to the actual surface of the actual geometry, right? And so you can do a one-to-one mapping of the pixels on your normalized geometry onto the surface of the target actual geometry, right? So that's one way. The other way is that you start off from the actual geometry, right? And as you iterate over all the normals in the fragment shader, right, that had been interpolated, you can point towards your normalized cylinder or normalized sphere and do a calculation of what pixel is it on the surface of your normalized geometry, right? And say, okay, oh, that, and then you can calculate that. Oh, this surface point, corresponds to this surface point on the cylinder or sphere, and then say, okay, well, I'm going to take the color of where this normal intersects my geometry. Or you can take a simpler one. You can start off from the center of your actual geometry out to your surrounding geometry, normalized geometry, sphere or cylinder, and then where it intersects the surface on that, grab whatever point or color is on that surface.